Hello. Today just we'll discuss regarding group of waves, which includes phase velocity and group velocity. Why this question comes? Regarding individual wave, when it propagates through the medium, then we see that everywhere its amplitude remains same. But if we talk about the existence of a particle in the medium, then sometimes we need to explain its existence with also some group of wave associated with the particle, so that only the particle where it exists, there only the wave will be present, and other place there will be no wave. That means we want to locate a particle with the help of wave associated with the particle. So if we assume that a single individual wave is associated with the particle, then everywhere the wave will exist. So this is not a proper way to explain the existence of the particle. Then concept will be there such that only wave will present nearby in the vicinity of the particle, and other place no wave will be there. Then how possible to explain this? We need a number of individual waves such that after superimposition of all these waves will be created in a way that here the resultant wave will exist and other place the wave will not be there. In this way, if we take a number of individual waves like this, and then also say something different wave like this, and so on, when they superimpose with each other, then it is possible to find a group of wave. This is known as group of wave. So when we talk about the group of waves, it includes individual wave. Now we'll discuss that how individual wave after superimposition create the group of waves. For that, first we go an individual wave, say y1 is given as a where k is a vector and omega is a frequency in space and time. We have considered here one dimension wave. So if we take this individual wave, let's see a concept is there, phase velocity, how it comes. This wave, the angular part is the phase. So if we draw a diagram, say at t equal to 0, the wave profile will be simply a sine kx, right? So in that case the profile will look like this. So position dependent, the position of particle in the wave is shown here at initial time t equal to 0. Say after a time t equal to say t plus delta t. So what of ds in that moment this wave may be shifted a little bit, and then it looks like this. So we see that as a whole, in this time, the wave profile is shifted such that if we take this phase of the wave, then after time delta t, the same phase is shifted a little bit here. So in this way we can say that the phase is shifting with time, and the shifting of phase of this individual wave can be termed as phase velocity. Now how we can determine this? Check once. So after time delta t, the equation of this y profile can be written as y dash, say a sine So, if we talk about the shifting of the phase, and if we assume that it is the same phase as before, then this two phase angle, this one and this one, should be same. So we get, in that case, after manipulation, then one can find here that delta x, delta t will be omega by k. What is this? It is nothing but the shifting of phase. So this term very reasonably can be termed as the phase velocity Vp is given by omega by k. So we get a relation phase velocity of the individual wave. What happens if we talk about group velocity? Some concept will be here that when you go for group velocity, then we will take some example. So we will take two waves. One is y1 equal to a sine kx minus omega t, and another wave very nearby in value of wave vector and frequency, say y2 a sine this. So if we take the superimposition of these two individual waves, what happens? Let's see. this. Then after simplification we get sin c plus d by 2 cos c minus d by 2. So we get these two. After simplification, we find that cancelling kx here, so only survive here, kx cancel, so we get, and omega to omega cancel, so we get delta kx cancels, so we get delta k by 2 x minus delta omega by 2 t and into sine k plus delta k by 2 x minus omega plus delta omega by 2 t, this equation. So we get this one part which amplitude senses here, so small a and sine, we get some k dashed x minus omega dashed t. So it is another equation of wave where a is the amplitude given as twice a cos delta kx by 2 minus delta y by 2 t. Now one important point is here. If we see this equation, here we see that the amplitude is not constant, which was initially for individual wave, amplitude was constant, but after superimposition of all individual waves, when it produces the group wave, the amplitude itself is also function of x and t. It means that in time and in space, amplitude will be different. So this amplitude also is itself another wave, and the phase of this amplitude wave can be treated as group movement. So if we take the velocity of group, so this is the phase angle of the group or envelope of the resultant wave. So in that case, if we want to see after a time delta t, after a time delta t, after a time delta t and distance say delta x, what is phase? What is phase? If you want to know this, then as before we have to write the phase angle. The phase is x will change x plus delta x, t will change by t plus delta t. So it will become half delta k x plus delta x minus half delta omega into t plus delta t. Now if we go the phase movement for this group wave, then these two phases should be same. So we get in that case half delta k x minus half delta omega into t should be equal to half delta k x plus delta x minus half delta omega t plus delta t. Okay. After manipulation, from here one can find that delta x delta t will be here delta omega delta k. What is this? This is nothing but the group velocity. Why this is group velocity? Because it relates the phase displacement of group wave with time. So group velocity Vg can be given as d omega dk. So we have two velocity. One phase velocity Vp is simply omega by k, and group velocity Vg as d omega dk. These two velocity we can find when a group of wave propagates to the medium. Now comes that how they are related. So for example, in a medium, wave propagates through the medium. So for individual wave is simply omega equal to kVp for a wave in the medium this relation. So d omega dk, one can write here Vp plus k dVp dk, or it can be written as Vp k dVp d lambda dk. Now, what is d lambda dk? Now, we know lambda equal to twice pi by k, where k is wave vector and lambda is the wavelength. So we get d lambda dk minus 1 by k square 2 pi. Okay, so we get ultimately here, therefore d omega dk, one can find Vp and minus 2 pi by k, if you put the value here d lambda dk like this here, so we get, after cancelling k and k square, 1 upon k and 2 pi is here, dVp d lambda, or we get, now what is d omega dk? This is the group velocity. So we get Vg group velocity Vp minus, this is basically lambda. So we get lambda dVp d lambda. So this is a relation between group velocity and phase velocity. Now, so we get Vg equal to Vp minus lambda dVp d lambda. Now, very important point to be noted here. If we take this, it looks that group velocity is less than phase velocity. But in that case, dVp d lambda should be positive. Means that the rate of change of phase velocity with lambda, rather this is some dispersive relation. If it is positive, or slope of Vp with respect to lambda if positive, then only group velocity will be less than phase velocity. If there is no change with respect to lambda of phase velocity, then this becomes 0. In that case, group velocity is same as phase velocity. And lastly, if the rate of change of phase velocity with respect to lambda is negative, or this dispersive relation is negative one, then group velocity becomes greater than phase velocity. So depending on the change of phase velocity with wavelength, we can classify the medium through which the wave propagates into 3 categories. One is uh, type of medium if dVp d lambda is positive, then we get Vg is less than Vp. In that case, it is known as dispersive medium. Case 2. If dVp d lambda is 0, means that there is no dispersion in the medium. For each and every wavelength, the velocity is same. Or if a composite wave is going through the medium, for each wave there is no change in phase velocity with lambda, then we call this media as non-dispersive media. In that case, Vg should be equal to Vp. So non-dispersive media. For example, sound through ear. Here, a composite wave of sound when passed through the ear medium, there is no change of individual wave velocity with respect to lambda. Then the air medium is non-dispersive with respect to sound wave. And case 3, sometime dVp d lambda is negative. In that case, Vg will be greater than Vp. This media is known as anomalous dispersive media. So in this way, we can find 3 types of medium through which the wave propagates: one dispersive, non-dispersive, and anomalous dispersive medium. So finally, we can come to the conclusion that when a group of waves pass through the medium, then 2 types of velocity is related to this propagation. One is phase velocity associated with the individual wave, and other is group velocity, which is the velocity of phase in superimposed number of waves. Number 2, the phase velocity is simply depend on instant value of frequency and k by this relation, but group velocity depends on the dispersive relation of frequency with lambda. And number 3, that the relation between group velocity and phase velocity is existing given by this equation. Based on this relation, number 4, we can categorize medium in 3 ways. One is dispersive medium, where group velocity is less than phase velocity. One is non-dispersive medium, where the group velocity is same. And third medium is where the group velocity is more than phase velocity. So this is known as anomalous dispersive medium. So in this way we can discuss the property of phase velocity and group velocity. So this is today our lecture's content. Thank you very much.